Hi, this is Nick Pizzi, and this is another video in our operational series of videos that we're producing for water treatment plant operators. I want to share this screen with you. Today we're talking about Lake Erie water treatment specifically, and because it's the time of the year when we tend to see dead zones in the lake. This is entitled Lake Erie Treatment Dead Zone versus Turnover. Specifically, we're trying to talk to operators about the difference between dead zone on Lake Erie and turnover on Lake Erie, how you can tell the difference, and what proper choices you can make to produce the best quality water. You know, Lake Erie, a little bit of history here, provides a lot of drinking water to millions of residents living in northern Ohio, Pennsylvania, New York, that type of thing. And even over on the other side, Canada, a lot of people are using Lake Erie for a source of drinking water. It's a relatively easy source water to treat for conventional water treatment plant issues. And by conventional, we're talking about mixing, coagulation, flocculation, sedimentation, standard filtration through dual media, high rate filtration, and then chlorination usually, or disinfection with chlorination, that type of thing. Nothing fancy, no ion exchange, no membranes, no water softening. This is conventional treatment. It's easy because there's sufficient alkalinity in the lake to allow the use of alum, aluminum-based coagulants that can help you meet the surface water treatment rule. The total ionic strength and DIC levels and pH ranges allow for the use of phosphates for lead and copper rule compliance. And the source water turbidity generally is low, and so is the natural organic matter, the NOM. Although the NOM is somewhat low molecular weight, so it's a little difficult to take out, but we generally can handle it. And the oxidant demand is low. So permanganate can be used for pre-treatment as an oxidant rather than chlorine, and so that helps with compliance with the disinfection byproduct rule. So because of these issues, Lake Erie tends to be very easy to treat compared to, say, someone on a flashy river that has to treat water that changes from day to day, or from hour to hour, for that matter. So let's talk about the excess capacity and how that lends to easy treatment too. Now, right now, when I'm making this video, this is the year 2020, August to be specific, right at the end of August. And there's excess drinking water treatment capacity going unused in northern Ohio. And we have resistance to regionalization by the municipal politicians. And of course, the dwindling population in this area has resulted in the fact that we have more water treatment plant capacity than we need right at present. So most of the Lake Erie water treatment plants are working at a fraction of their capacity. Now that can be a problem because this excess capacity adds to the ease with which operating staffs can meet water quality requirements. Most operators on Lake Erie come to the water plant knowing that they have the luxury of, if they make a minor mistake, they can easily fix it because they got a lot of time. The water's moving rather slowly through the plant. So these things make it rather easy right now to treat water on Lake Erie. Is it too easy? Should we talk about that a little bit? I like this particular topic, so I want to discuss it a bit. It'd be interesting to know 10 or 20 years from now if things are still as easy as when I made this video. I hope I'm around to hear from you. The chemical, physical, and biological characteristics of Lake Erie water don't vary from day to day. Unlike, again, on a river water supply where it might change every hour. Typically, you can come into Lake Erie and take your laboratory analysis each day, and things very rarely change. pH, alkalinity, hardness, all of those things stay the same from day to day to day. It's like a problem for monotonous. That's the word I'm sure you're looking for, sorry. So in addition to that, the intake placement in deep water away from the shore and away from the influence of rivers and streams that enter into the lake help also to make these Lake Erie water treatment plant operators see the same quality of water day after day. So most of the variability of Lake Erie water chemical and biological characteristics are seasonal. The variability is seasonal, and therefore it's going to be predictable. We know that it's summer. We're going to look at a certain kind of water. Yes, things are going to change, but that's not till the fall. We have several months to prepare for it. We can get our basins cleaned out, for example, because we know that next month things are going to start to cool down a little bit. In a river plant, you might not have that luxury. So it makes it easy to have these variabilities seasonal only. Now, predictability, of course, can lead to complacency, and therein lies the problem, I think. So we have these Water treatment plants that are sitting rather idle almost in their treatment capacity, and the predictability of the raw water quality makes it very easy for an operator to become complacent. You come in day after day, month after month, year after year, and things just don't change that much. So it's easy to think that we can come to work without knowing, with knowing that we're not really going to get challenged. So we don't really have to change treatment strategies in a large sort of way. So moving along, I want to make this commentary. As I'm preparing these slides, which is again late August of 2020, the plant operators are halfway to the end of another Lake Erie dead zone season. And we've seen that rear its ugly head in the last few weeks. Dead zone is an annual occurrence when water treatment plants in Northeast Ohio have challenges in controlling the water quality output from their conventional water treatment plants. We've seen consumers complaining about yellow water recently, taste and odor at the tap. That's within the last couple of weeks through several water treatment plants. Now, the frequency and severity of these dead zone events, along with the more traditional Lake Erie turnover events, seems to be increasing on Lake Erie. Now, this may be due to the climate change which we're going through. It's producing warmer and drier atmospheric conditions that can change the temperature of Lake Erie. In fact, the data shows that Lake Erie mean temperature is increasing over time. And Ohio's political failure to adequately control the farming operations in the northwest portion of the state, where the farmers continue to dump the fertilizers in the Lake Erie watershed. The failure to control that is causing us a problem also. That's creating more dead zone issues. So because of those things are changing. Let's talk about that, and so that we can set the historical timeline for ourselves. I'm going to talk a little bit about my experience from the 1970s to 2020, this year right now. That means I've been around for 45, almost 50 years now, and in that time I've seen things change. So let me talk about that. It'll be interesting to know what happens 10 or 20 years from now. When I started in the 70s, I was a chemist. So I analyzed the quality of Lake Erie water daily at the water plant that I worked. Of course, in the 80s and 90s, I worked as a manager of several Lake Erie water treatment plants. So I treated the raw water daily. And then from 2000 on to present, I'm a consultant. So I work with clients who operate Lake Erie water treatment plants. So I've been around to see how things have stayed the same and how things have changed. And I need to talk about that a little bit so that you have some timelines to work with here. Almost every year now, I see at least 2, maybe 3 treatment challenges crop up at one or more of the Lake Erie water treatment plants that tends to result in less desirable drinking water. We have dead zone water and we have the turnover water, and I want to discuss the difference between the two. That's what we started out with. I want you to know how to tell the difference between the two and how to treat them properly. Each of these presents a unique challenge to the operator. Each has its own unique treatment requirements, and that's the important thing. I'm finding that the operators are trying to treat this water, one of these waters, the same way they treat the other water, and that's not possible. There are 2 different unique forms of treatment requirements. And this video, of course, is going to try to memorialize those techniques for future operators. If things continue along this path, I think it's only going to get worse. So I want to make sure that we have this down and recorded in for history. So what's changed over time since I've been in this business on Lake Erie? The overall quality of Lake Erie has improved from what it was in the 1970s, believe it or not. When I started, Lake Erie water quality was comprised of industrial, commercial, and municipal discharges that weren't regulated back then. When I started, there was no NPDES system. There was no combined sewer overflow mitigation. There's very little knowledge at the time of pollutional effects from homeowner lawn and landscaping chemicals that we used. And also the increases in the boomer generation, which I'm a part of, coincided with the aging post-World War II wastewater plants that resulted in frequent sewage bypass events. Back then, when a huge rainfall would occur, the wastewater plants had no other way to go about things other than open their bypass valve and let that raw sewage go straight in the lake. So Lake Erie was in bad shape back in the early 70s. And so, you know, regulatory people came along and started changing those things. I can tell you personally that swimming in Lake Erie beaches often resulted in ear and sinus infections for us kids. Very not unusual to see sightings of human pollution at the beaches when we were swimming. And I'll leave it at that. Lab analysts on Lake Erie were required to analyze for that pollution back then, which in turn provided operators for the information that they may not have these days. By that I mean, we were required to test for things that no longer are required to be tested for. That makes sense to you. The things that we were required to test on raw water daily on Lake Erie tended to give operators a heads up advantage to know what was coming down the pipe, but you don't do today. So let's talk about those a little bit, because that will help you understand this information I'm going to present. Lake Erie raw water quality at present requires the lab analysts to perform daily and weekly tests. They give the plant operators a chance to take that information and process it for the source water to make drinking water out of. However, because raw water, Lake Erie water was subject to frequent discharges in the 70s, the Ohio EPA and Ohio Health Department required water lab tests for parameters that they don't require today. Specifically, back then we had to test for dissolved oxygen every day. Some plants do that today, but most of them don't because they're not required to do that. But when I was testing for dissolved oxygen, I knew when pollution was coming our way. I was able to tell the plant operators, you know, the oxygen in the water is going down. It's trending downwards. We've probably got algae die off. We got this, we got that. We would know what to do for it. Nowadays, if you're not testing for an oxidant or oxygen demand, at least you don't know that information. Back then, we were required to do fecal coliform or fecal streptococcus on membrane filters. That, of course, helped us determine the presence of human pollution. They don't do that anymore because Lake Erie is just not that bad to find fecal coliforms all the time. We had to do taste and odor tests daily, but do algae counts daily. Now, I know a lot of plants do that, but most don't, especially the smaller places. So back then, we were able to tell the presence of algae and the types of algae that were coming. So we knew that if filter clogging algae were coming or taste and odor algae were coming, we could do something about it. We also knew by the pH and the algae present whether they were dying off, whether we were going to get a dead zone because of it. So we knew to put on the activated carbon and increase the coagulants. So because of that, because of the lack of information that you have now, I want to educate us all on the stratification, turnover, and dead zone issues that big bodies of water like Lake Erie tend to go through. Now, Lake Erie water tends to show a difference in water temperature depending on the depth of the water and the time of year. Lake Erie goes through a process where it forms distinct layers with different temperatures, and scientists call that stratification. In other words, there are layers of water as you go down further and further into the lake where the water temperature changes and stays within that particular layer. You can go from one layer to the next, changes temperature. Now, these different strata tend to have different densities because of that different temperature. And then when they get enough difference in temperature between each other, they're going to mix poorly. If you aren't fortunate enough to take in one of these zones, such as a dead zone, then you're going to have your treatment challenges cut out for you. But because they mix poorly, this is what happens each year. In the winter, ice is the coldest at 0 degrees centigrade and it's less dense, so it's going to float on the top. Slightly warmer water at 4 degrees centigrade, water underneath it, which is more dense, sinks to the bottom of the lake. In the summer, the opposite happens. Water warmed by the sun is less dense and floats on the top, of course. The sun can only penetrate so far, and so the lower layers of water stay cold, therefore denser, and it's going to sink to the bottom. Now, when that water gets to the bottom, it has organic material in it, especially when the algae begin to die off and the dead bodies sink to the bottom with that cold water that's drawing them down. Those become sewage. Basically, they start to eat up all the oxygen. So the water, the layer of water down at the lake bottom becomes anoxic. So any minerals that are down there are going to become anoxic, and that's what we've got to talk about. So let's talk about the anoxic layer and manganese, which is a problem for operators. And iron too, we're going to talk a little bit about iron. It's a similar situation. If you have manganese in your source water, you need to turn it into a flock to get it out. It'll turn into a yellow flock, and when it's fully oxidized, and that flock needs to be settled and filtered. So basically, for you chemists out there, we're going from the oxidation, the ferrous to the ferric, and the manganese to the manganic or manganic form. So we take that anoxic form, that ferrous form, add oxygen or add the chlorine to oxidize it, becomes ferric, becomes a flock material that we can see, no longer soluble, it's insoluble, and we can filter it out. Now, when it comes to manganese, unoxidized manganese or manganese, time and pH have a relationship that was going to affect your operations, and that's where we see operators getting into trouble these days because these things are happening more frequently. pH has a direct effect on the amount of time that it takes to oxidize manganese. And remember, When unoxidized manganese comes to your plant, it's colorless. When you oxidize it, it turns yellow. And if it takes a long time to turn it yellow, it goes through your water plant and gets into the distribution system before it oxidizes, then it's going to turn yellow. And then you never saw it coming. You never saw it going, for that matter. Let's talk about that pH. And I got this information years ago from a gentleman by the name of William Naki from the southeastern portion of this country. He's the expert on manganese control, wrote a book about it. You should get that copy for yourself. I had dinner with him one night and he taught me a lot of interesting things. One of the most important things he taught me is that you've got to know your pH if you're going to try to take manganese out of the water. Because at a pH of around 7 or 7.1, it can take weeks to oxidize the manganese in the water to the yellow flocculent form that we got to filter out. It can take weeks at the normal chlorine residuals that we keep in the water plant. If we can get that pH up to 7.4 or 7.5, it should take about 20 minutes or so. You get it up around 8, it's going to take a few seconds, maybe even a minute or so. Therefore, I would want to have caustic in my rapid mix if the pH got low enough and I knew I had manganese coming in. So I would keep the pH up in the rapid mixer and the flocculator as my strategic defense to get rid of manganese that I can't see because it's colorless. It's manganese when it comes in. I can't see it. It's dissolved. I've got to change it to manganic by adding the chlorine, and I got to get the pH up to do that. So the fact that there are more than one variables when it comes to manganese, you've got time, you've got temperature, you got pH, all of that, those variables change. Very difficult for operators to keep on top of this. Often they make mistakes when they're trying to treat for manganese. Number one, because they don't know they have it because it's colorless. And number two, because they're making the wrong decisions when it comes to treating this. So let's discuss that. And also while we're doing that, let's discuss the difference between turnover and dead zone, because that's important. Two different things. Turnover. Turnover usually happens in April, in the spring, and fall in November. Now that may change. I'd be interested to know 20 years from now if that changes a little bit, but in my experience, the lake turnover, any turnover in a big body of water like Lake Erie is going to change in April and November. That's because these two separate layers begin to reach temperature equality, and so the water starts to mix a little bit. The temperature of the water is important here. Turnover is typically characterized by high turbidity, little or no change in the water temperature, and chlorine demand. That temperature is starting to reach that 4 degrees centigrade mark. And to treat this, we want to add potassium permanganate, we want to add caustic at the rapid mix and some chlorine there too, and we want to increase the coagulants. Equalized water temperatures means that almost all of the water treatment plants in the neighborhood are going to see this turnover, so you might want to get on the phone and start calling people. We'll talk a little bit more about the treatment as we go in future slides, but first let's contrast that with the dead zone water. This usually happens in the middle of summer during hot, dry spells with little or no wind, and that's going to be August and September. If it's August or September on Lake Erie, and you're in a water treatment plant, expect a dead zone. If the temperatures have been hot, the days have been calm, no wind, the water's not churning, it's dead still, the turbidity is low, you might get that dead zone. If it's August and September, think about that. Be prepared. These are characterized by a quick drop in temperature as opposed to the slow change of temperature for the turnover events. Quick drop in temperature, usually you go from 25 or 26 degrees C, all of a sudden you find that you're in the teens. The drop in pH happens also at this time. You'll get down around 6, 9, or 7, but the alkalinity often doesn't drop with it. At 15 to 19 degrees C, you're going to have a mix of anoxic water coming in, and at 14 degrees C, it's pretty much dead zone. So at 15 to 19, if you go from 25 degrees to 15 or 16 or 17, you got a problem. You got to start changing your treatment, and you don't do it the same way you do with turnover. I'm trying to make that clear here. The treatment would be to add caustic or soda ash because you got to get the pH up in the rapid mixer and the flocculator. The goal would be to keep that flocculator up to at least 7.5. You got to get your pH up with the caustic. You got to increase the chlorine feed into the rapid mix because you're going to have to start oxidizing this manganese. You got so much time to do it. You definitely want to do it on the pre-treatment side. You want to increase your coagulant and also the powdered activated carbon. And if you're going to use permanganate, I got a word to say about that. That's fine. But remember that permanganate is a very weak oxidant when compared to chlorine. Now, I know you don't want to put chlorine on because of the trihalomethane issues, and I respect that. The chlorine will oxidize manganese much more quickly, much more readily than the permanganate does. And when you add potassium permanganate, you're adding more manganese to the water. If you keep that pH too low, which often happens to operators, you're going to get manganese in the system. And days later, you're going to get yellow water complaints. If you're going to use the permanganate, that's fine, but you better be on your toes because it will get past you in a heartbeat. So think about it. The great difference in water temperatures between the strata means that there's going to be very little mixing. And so a dead zone can remain intact and hit one intake while not hitting another, as opposed to the turnover when everybody tends to go through it at the same time. The dead zone tends to float out there as a distinct body of water within a large body of water. It tends to hover over one intake and not the neighbor's intake. You can call your neighbor and say, are you experiencing any problem? No, I don't see any problem. But you might be having the problem because that blob of water is floating around seeking out an intake to come into. Maybe you, maybe the next guy the next day. So let's talk a little bit more about dead zone manganese pH and treatment. Where does this manganese come from? Well, it could come from the permanganate that you're adding. It could come from your own sedimentation basins. If you're recycling sludge, you know, that sludge sits at the bottom of your sed basin. That's like a mini Lake Erie that becomes anoxic also. If you recycle it at the wrong time, you could be sending reduced or manganese back to your rapid mixer. And again, you got to go through all what I've just talked about. But it also is going to come from the lake bottom, especially during these turnover events. So manganese, of course, manganese ingestion, and they're studying this today in 2020. They're studying a disease called manganism, which is a central nervous disease. Because of that, I think the manganese is likely going to have an MCL associated with it in the future. Right now, it's, of course, it's a secondary MCL because of the aesthetic effects. But there are people out there trying to prove that there's a health effect. And if it becomes faith and gospel, you're going to be treating this a little different way in the future. How do you remove the manganese? Let's go over that again. Because you have to oxidize it. You have to go from the elemental state to the flocculated state, which turns into MnO2 or manganese dioxide. That's the manganic state. It's a solid flock particle. It's going to settle and it will filter because it's a precipitate. It'll be the same for iron. Iron oxide is a precipitate also. Of course, that has to take place before filtration. Otherwise, it's going to get into your system and turn yellow out there rather than where it belongs, which is in the flocculate. What's the single most important factor that regulates the speed at which manganese turns to MnO2? And again, the answer is pH. Time is needed for manganese to oxidize into MnO2. If the pH is low, the time it takes will be weeks rather than minutes. Perfectly fine looking water can leave the plant only to turn yellow over time in the next couple of days if the manganese has not yet oxidized. And I've seen that happen this year. I saw it happen last year. I've seen it happen many years. What looks like good water leaving the plant starts to generate phone calls 2 days later because the manganese that you didn't catch is now being oxidized in some water tower out there. Now you can't afford to change the pH in the clear well. You can't afford to try to kill off the manganese because when you do that, it's going to turn into a flock particle, which looks yellow, and then you got a problem. You have to do it on the pre-side. So there is no clear dose of caustic feed that I can give you that fits each situation. You need to shoot for pH. So don't worry about dosage when it comes to manganese. When it comes to caustic to fight manganese, worry about the pH. Do not keep the pH down around 7.69, 7.71. It's too low. Don't even go to 7.2. Make sure you get it up to 7.5. Good rule of thumb would be in the last stages of the flocculator, you should still have a 7.5 pH. If you do, I guarantee you that manganese that's in the water is going to be oxidized, assuming you've added enough chlorine. You can expect customer complaint calls if you keep that pH down around 7 or 7.1 or 7.2. Get the pH while you still have the chance. Now, this should be a standard procedure for every August through September in every Lake Erie water treatment plant. You should have, the operator should know that it's time to get the caustic ready to go. It's July, let's get the caustic out. Let's set it up. If I don't have an automatic feed system for caustic, I set up a manual one in July so that when August comes, I'll be ready to go if I hit that dead zone water. Coincident with that, every operator should know to watch for temperature. Temperature is an easy measurement to make. And temperature is easy, but it's also complex. Think about where the temperature is that you're adding, that you're measuring. Temperature in Lake Erie is what's important. When it gets down to that that certain temperature. If you see a drop, then you know you got to do something. So in the small plants versus the big plants, you might be looking at lake temperature versus the water temperature coming out of the plant. I think you understand what I'm talking about. The point is, when it gets to that low, you know you've got the dead zone issue. Put the caustic on right away. More discussion of turnover versus dead zone occurrence. Again, lake turnover water typically is going to occur in April and November when the layers of strata in Lake Erie water are 4 degrees centigrade or about 39.4 degrees Fahrenheit. That's where it's its highest density. Operators are going to see a gradual temperature change. The water is either going to work its way down gradually to 4 degrees, or it's going to work its way up gradually to 4 degrees. It's a slow, gradual process. It takes weeks. So you know it's coming. You see it gradually getting to that 4 degrees. When you get to 4 degrees, you're going to get turnover out in the lake. This is lake water we're talking about, not in the plant, but lake water. The source water turbidity is usually going to increase because the mixing zones out in the lake can be quite intense, quite violent. You're going to get higher turbidities. That's opposed to the dead zone water. The dead zone water typically is going to occur in August and September, as I mentioned, when the water is about 25 degrees or so. And there have been stretches of very warm weather and cloudless days, allowing the sun to penetrate and warm the water to a greater depth. The operators are going to see a quick drop in water temperature. I mean, within their shift, temperature is going to go from 25 or 26 or 27 degrees centigrade all the way down into the teens quickly. You see that, it's dead zone. Get the pH up. You let it get down, or I'm sorry, if it gets down to 14, I know you can't change it, but if it gets down to 14 degrees centigrade without you doing something, you're in a world of hurt, trust me. Here's a chart that explains density of water. It's a quirk of nature, and I'll talk a little bit to the chemists here. You know, if you're a chemist and you wrote out the water molecule on a two-dimensional piece of paper and you put that oxygen there and there's 2 hydrogens, you might expect to see a 90-degree angle between those 2 hydrogens and the oxygen, but it's not true. More like 104.5, 105 degrees rather than the 90 degrees. And that's because of the hydrogen bond. The hydrogen bond makes water, actually, it makes it a polymer out of it. 5 or 6 chains of water molecules will react with one another, link up like a polymer. And these hydrogen bonds will generate a vibratory effect within a weak energy being put in the system. So when you have water that's warm, you've got a lot of energy water from the sunlight putting in the water. But as you start to lose that temperature, as the water starts to go down close to 4 degrees, like any other liquid, it becomes denser and denser and denser. Eventually it would freeze at its greatest density. And then the dense product would have the most density and sink to the bottom, but that's not true with water. As you lose that temperature, that energy in the water and get close to 4 degrees, that hydrogen bond puts in its own small but unique form of energy. It causes a vibratory effect between those hydrogen. They actually vibrate in space in that 3rd dimension. And that energy is enough to make water denser as those molecules close in on one another when they tend to freeze. And that's why the ice floats. It's less dense than it is at 4 degrees. Otherwise, all the ice that formed millennia ago would have sunk to the bottom. The lake would be a little different than we know it. So note, I think I have the temperature there, right at 4 degrees centigrade. It's at its densest. On either side of that, it's less dense. So think about that and the effect it has on your treatment process. So let's summarize. This is a rule of thumb. And again, study all of the other videos that I put on for you, but this one for dead zone, very appropriate right now. We need to know the difference between turnover and dead zone. April and November for turnover. Lake water drops to 4 degrees, gradually approaching it, either going up or going down. High source water turbidity, little or no pH change. Alkalinity and pH tend to track each other, whether they're going down or going up. They stay in unison with each other. You can count on that. You need to use PAC and increase your coagulant and permanganate, as opposed to dead zone, which happens in August and September. Sudden drop in temperature, water plummets from the mid-20s down into the teens. Very little source water turbidity, pH drops to 7 or 6.9, or maybe 7.1 maybe. Often the alkalinity doesn't change. You see a drop in pH, but the alkalinity stays up. It's very strange. And I've seen operators report that, and I've seen it myself. Anoxic water down there needs chlorine and caustic on the pretreatment side, powdered activated carbon also, lots of it. Shut off the permanganate unless you're very confident in what you're doing with that permanganate. So with that, we'll close out. Say thank you. That's all we have today. Good luck.